When forces act on objects, it can be useful to draw a diagram to describe how they're acting on those objects. We call these types of diagrams free body diagrams. And we start by isolating the object that we care about and just drawing that object in a coordinate system. We then include all the forces acting on the object as vectors, so as arrows acting on that object. And frequently, in order to do useful things with that, we have to resolve those onto our coordinate system, into x and y components. As needed, we can draw additional free body diagrams as well. For an example, here we have a skater. This is a top view. And we have one person pushing on one side and another person pushing on the back. We want to draw a free body diagram that shows these forces acting on the skater. So we start by drawing the skater. I'm not a great artist, so I'm just going to draw it as a point. This is a particle model, and the particle model just means that all of the mass is concentrated at the center of mass of the skater. So this is a useful model that lets us describe translation. It won't let us describe the rotation of the skater if the skater were to try and do spinning stuff. We need a different model, like a rigid body model or something. But for describing the translation of the skater, just as the skater moves around, this should be sufficient. And then we draw the forces acting on the skater. So I've got that dot and force 1 and force 2. You'll note I could have drawn the forces acting onto the dot with the arrow pointing at the dot. Here I've started them on the dot and are going away from the dot. Either way is fine for a particle model. It doesn't care as long as it's on the correct line of action. We then have that coordinate system, x, y, so we'll call that my coordinate system. And then we can, if we want, write our forces in that coordinate system. This vector is magnitude of 30 newtons in the i-hat direction, so that's in the x direction, and F2 is 40 newtons in the j-hat or y direction. If we want to add these forces, we just do a vector sum of those forces. Here, that means we can add the components. Since there's no i-hat component of one and no j-hat component of the other, this is fairly simple. We end up with the i-hat and the j-hat component separately. They add, there's our net force. And so that net force, if I want to represent it as a magnitude and direction, it's the combination there with some angle theta, where you can get that magnitude as the sum of, basically it's just the magnitude of this vector. So if you have x and y components, you can add them in quadrature. This is squaring each component, adding them, taking the square root. You can think about it as the Pythagorean theorem of a right triangle here, where you've got the bottom leg, and then F2 would be the right leg of this right triangle. And similarly, for getting the angle here, we can take the inverse tangent of the opposite over the adjacent side. So if you want the angle with the x-axis, that's the y value over the x value. So the y component over the x component. And that's a free body diagram with a little demonstration of adding forces and getting a resultant force from adding these other two forces.